1.5. All right, so concavity. Let's talk about generally a graph in terms of a real graph that we all can relate to. We have looked at some graphs of cubics, and some of our graphs of cubics look like this. Would everybody agree with that? Where we have a maximum, we have an inflection point, and we have a minimum. So when we did the second derivative graph, a cubic becomes a what when you do a derivative? All right, so this is the original function. So the first derivative graph, first of all, will have a x-intercept at the max and the min. And then it has a what to showing on the first derivative graph for the inflection point. Right, that inflection point turns into a max or a min. Now in this case, I don't really know for sure where I should put that on whether it's going to, do what until I label my original problem. Like, I don't know whether to make it open up or down. So this is increasing all the way up to this max, right? Increasing would be above the x-axis. Would everybody agree with that? And then it starts decreasing from the max to the min. So since it's decreasing in that area, I know it's going to be all below till I get back over here to this min. So now I know which way it opens. And then I also know that it's going to increase over here, so my third piece of my graph is above the x-axis. So my graph actually ended up in 3 parts because it increased, it decreased, it increased. Now, does everybody agree with that? All right. But again, this point down here is my inflection point that looks like a max on this graph. Everybody agree with that? That's what we've discussed so far. Well, today, I want to take it a step further. So if I took the derivative of that equation, my quadratic would become a linear. Okay. And when you do the second derivative, any place it crosses the x-axis is an inflection point. I might have just drew that the wrong way. Let me think that again. Don't draw that yet. I was just drawing and not thinking. Cut that out. All right, let's go back and let's look at this problem and make sure that we think about concavity on each side of the inflection point. All right. A maximum is what we call concave down because the bowl is opening down. And a minimum is concave up because the bowl opens up, so you can put stuff in it and it wouldn't fall out. When the bowl's upside down, everything falls out. Concave up and concave down is the same concept as increasing, decreasing. Concave down means everything has to be below the x-axis. Concave up means everything has to be above the x-axis, so I had it right the first time. And I was just drawing something. So I am below the x-axis until I get to the inflection point here on the x-axis. And then I'm above the x-axis after that because it was concave up after that. So I can see where that inflection point moves. Now on here I can see this was my max and this is my min because I know it changed from positive to negative and it changed from negative to positive for the min. But over here, I don't see anything about the maxes or mins. All I see is about inflection points. So that's what our second derivative graphs are going to show. Now, once in a while, if you have a high enough power problem with enough information in it, an inflection point might show up on a first derivative graph as an x-intercept, which would be kind of a misnomer because they usually don't show up on first derivative graphs as that. they show up as maxes or mins. But sometimes they'll end up being an intercept. It still might look like a max or a min, but it'll be an intercept. And then when you take the second derivative, you realize, oh, that really is an inflection point because it came out in the second derivative as well. The other thing is, sometimes in your first derivative graphs, or even doing your equation work, your table will show that too with the sign chart, because in the first derivative graph, when the sign doesn't change, you know it's an inflection point. Unless you've already determined it's a cusp or a vertical asymptote or something like that. So that's kind of the progression of how you can go from the original problem to a first derivative to a second derivative and see where are the items located that are critical to the graph. Now, we'll focus a lot more on that. There's an activity I have, and I told y'all about this the other day, where I'm going to give you a first and second derivative graph. You're going to label, kind of like, you know, this part up here is your increasing, this whole piece down here is decreasing, this whole piece over here is increasing, so you can figure out what all these pieces are. And then you'll label it over here as well, that this over here is concave down because it's in the negative region, and this one over here is concave up because it's in the positive region. And you'll take these two descriptions and go hunt for the graph that looks like the original problem without having an equation. And then we'll try to match the equations up and the description of all the different parts that you come up with, the maxes and mins, inflection points, and I think there's one more thing. So I think there's like 6 different things you can match together, if I remember correctly. But you're only going to get part of it at a time. And so we'll probably start that, I'd say the first of next week. I'll hand out the first and second derivative graphs and let you get them all labeled up. And we'll put one problem per page because we have a lot of description stuff to write down and put together. That way we won't have to worry about spacing. All right, now let's go into actual lesson today and doing the math. If we have equations, we can do the math and find this information. Let's start off with the definition of some things and what the tests are for. Concavity. Let F be differentiable on what kind of interval? Open. Always open for differentiable. What's closed always work with? Kind of. It's really based for the continuity. We usually talk about closed for the continuity for the graph. And the graph of F is concave up on I if the first derivative is increasing and concave down if the first derivative is decreasing. And I'm going to illustrate both of that for you. All right, I may come back and put something in there. I need to go look something up, but I'm going to draw these graphs first. All right, so when you look at a graph like this, this one is concave up. And this one is concave down. For a graph to be concave up, your second derivative must be positive. So that means your second derivative would show on each side of your max or min that it's positive. When your graph changes from positive to negative, it causes an inflection point. So when your graph stays positive forever, that proves there's a max somewhere in there. And then when your graph stays negative, it shows that it's concave down on both sides of your maximum. So I'm talking about the second derivative value would be, this whole side would be positive, and the other side would all be positive on each side of your max or min. Is how you got to look at it. So for this minimum, both sides would be positive, and on this maximum, both sides would be negative. Just to throw in one other thing that I don't have in my notebook, but if it's an inflection point, then this side would be negative and this side would be positive because it changed concavity. To go through an inflection point, it always changes concavity. And that's why the second derivative is all about checking inflection points and not really checking maxes or mins. So just going to double check one little thing about what I wrote here. I'm going to make sure that that's supposed to be a first derivative mark. Pretty sure that's right. But you know, I recopied these notes and I could have recopied it wrong. No, they're first derivative marks. Yeah. So what this is saying is when you have your first derivative showing increasing, that should show that it's concave up on both sides of your inflection point. And if it's not on both sides of inflection point, but on both sides of some point. And that if you're decreasing, it shows it's concave down. So we're going to go through some problems and see how to use this information. But the main thing is to remember, if it stays positive on both sides, it's concave up on both sides, makes a minimum. If it stays negative on both sides, then it's concave down, makes a maximum. And if it changes from positive to negative, that makes an inflection point on a second derivative chart. And then the second thing you need to know is that in words, but I think the visual is much better than the words. The words just say that if the second derivative is positive, it's concave up, and if it's negative, it's concave down, and they just use symbols. And when the derivative is 0, that causes an inflection point. So I think I've illustrated that better than I could write it in words. So I think we'll just go with the illustrations. So what we're going to do is do a few derivatives, and some of these may get a little bit nasty, depending on what kind of problem we've had. So if it gets too nasty, we might look at putting one in the calculator. The first derivatives are never bad. It's when you get to the second derivative sometimes that causes them to kind of be really bad. But we can make them better if we think smarter than what I wrote on my paper. Wow, I did that one the hard way. We'll do it the easy way. All right, so in example number 1, we're going to determine the open intervals on which the graph is concave up or down. All right. So in order to do this, we need the first derivative and we need the second derivative. And later on, when we get into actually wanting to know more information, we might need to make a chart for the first derivative and the second derivative. But for this problem, because it only wants to know when does it change from concave up or down, we only have to do a chart for the second derivative. But we still have to find the first one, because you got to have it to get the second one. So first, if I leave this problem the way it is, I can do chain rule. Put the power in front, makes it -6. That makes the power go down by 1 to -2. And what's the derivative of the inside? Okay. So I'm going to multiply that 2x to the -6 and get -12x, x squared plus 3 to the -2. So that's the end of my first derivative. Now, if I was wanting to do more with this, like if I was going to make a chart or something, I might clean that up, move the negative power down. But since I'm not making a chart with this one to find any extremas, I'm just going to go ahead and leave it in this format. Now, I can't do this one exactly the same way for the second derivative, because in the second derivative, I have a product that has a letter in it. See, the product before had a number in front, -6, and that didn't affect my derivative work. But this time I have to really do product rule or quotient rule. Because I could bring this down and make that positive power, and that would be quotient rule, but I think product rule would be easier. Because after looking at my paper, I think product rule will be easier. So we're going to try product. So we're going to write down the first. We're going to come back in a second and take the derivative of that second piece. But let's go ahead and get the whole thing written out first, because that's the part that takes a little bit of extra work. Plus, write down the second. And what's the derivative of the first? Okay. See how much easier it is if you don't stop to do the derivative of the chain rule piece and you just fill in everything else first and come back and do the chain rule? Now, the chain rule is going to just be on this part. Oh, I've spot the lid. Yes, I heard you and I wrote X anyway. Thank you. Yes, it's just -12. All right, so... And that -12 cannot be multiplied into that parenthesis, so we'll deal with that part of the problem in a minute. It does need some cleaning up, but we can't clean it up till we get this first piece done so we can know where we're going with it. So to do the chain rule of what I put in the box means put the power in front, take 1 off the power, which makes it -3, and the derivative of the inside is still 2x like it was before. So now I have 3 different items that are outside that cubic, and that cubic's going down because now's the time to put him on the bottom. So we're going to do -12x times -2 times 2x. How much will that be? That's right, 48x squared, right, because I got x times x? Yeah. And then over there, all I really need to do is just bring it down and make it a positive power. And I didn't make that negative go anywhere because I'm still going to do something over there. So I thought I'd leave that negative on the 12 until I'm done doing what I need to do. Because what do I now need to do? Right. So once I get this common denominator worked out, which I think is a lot better than what I did with the quotient rule. Right, I need 1 more of these x squared plus 3's to make it cubed. So now I'm going to have 48x squared. I'm going to distribute that -12 and go minus 12x squared minus 36. And I have actually got like terms now I can put together. So the final answer to this derivative, the second derivative formula, is 36x squared minus 36 over something cubed. You want to take a 36 out? Might help. Okay. We can take a 36 out. Well, if you see some simple factoring you want to do, you can just go back and erase something and fix it. You don't have to rewrite the whole problem. Alright, so we got it all factored out. Got it down to the final answer of what it needs to be. So, that's interesting. I don't have the right answer on my paper. I lost a power somewhere. All right, so the denominator, is it ever going to make a vertical asymptote? Everybody agree? No? Because it can't be 0. So all I got to do is worry about the top. So on the top, if I think about that being x minus 1, x plus 1, then it's obviously 1 and negative 1 are my two inflection points. So once I find my two inflection points, I'm supposed to do a chart. The chart is very similar to what we did with the first derivatives. It just finds a little different information. So the first line is going to be your intervals, just like before. So my first interval is going to be from negative infinity to negative 1, and then from negative 1 to 1, and then from 1 to infinity. And then we're going to choose some values to put in the second derivative so that we can evaluate to see if it's positive or negative in each region. And like before, we'll have our signs, the little pluses and minuses. But now the last line will tell about concavity. Is it concave up or down? So the only difference in this table and the previous table is I'm using second derivatives and I'm telling concave up or down instead of increasing, decreasing. Does that make sense to everybody? Just a slight difference on our sign chart. And we've got to pick some values. So what do you want to use for this first interval? Okay, negative 2. What do you want for the second one? 0 is a good one. And how about positive 2 for the other one since you used negative 2? Because usually, with some of the, well, not usually, but a lot of times there'll be some kind of symmetry with these numbers, or there'll be one's positive, one's negative, or something like that, and you'll realize you're using similar numbers. All right, so plug that into the whole entire derivative. And best way to probably do that is to put it in the table calculator y equals and go look them up on the table, or do the value button. Now, no matter what we get with this, y'all, I hope we're not getting 0. Because if it is 0, then that would tell me something's wrong with my derivative. Yes. Let me pause the video and go get you some batteries. So, what did you get for negative 2? Positive or negative, that's all I need to know. Okay. We won't write the decimal on the board, but you got it on your paper. So that means that it's up. All right, what's the 0 give you? Negative. So that means it's down. And then you got positive on the last one, which means it's up. They were the same decimals. So that's good to know because that tells me a lot. So here's my inflection points on where it changes its concavity. So it's telling me it's concave up, then it's concave down, then it's concave up. Not exactly that idea, but you kind of get the idea. You might have some x's and mins in there, I don't know. That's all the concavity's telling me. See, the problem with this chart is it doesn't take into consideration maxes or mins, because this up over here could have a max going on in the middle of it, which is why the inflection point might come next. And this down might have a minimum happen sometime in between it. So because of that, it varies a little bit. Now, let's look at one more example of this thought. All right, so in this problem set, we're going to take the first derivative, see what we get, take the second derivative, see what we get. We know already there's something going on in the denominator at what? Positive 2 and negative 2? We just don't know if there's going to be any inflection points to go with those vertical asymptotes. Well, we know that before we even start any derivative work, because the denominator is already here. So we're just doing the derivative work to see if we can get anything out of the numerator. So write down the denominator. The derivative of the top is 2x plus, no, excuse me, minus. God, I've got to turn around. This thing's choking me. Write down the numerator. Take the derivative of the denominator, which is 2x. So at least the derivatives are easy. And the denominator squared. Now, the more you can simplify this, the better the next one will go. Because when you start doing the next one, you're already going to have something that's probably pretty complicated to do as well. All right, so 2x to the third minus 8x minus 2x to the third minus 2x, all over our denominator squared. The cubics are going to drop out, so I have negative 10x over x squared minus 4. Now, if I was looking at doing more than just concavity right now, I could possibly look at the derivative here a little bit. So, for example, in some later work that we might be looking at, we might set the numerator equal to 0 here and find there's a max or min here, because negative 10 x equal to 0 would be x is 0, and there might be a max or a min there. Does that make sense? So keep that 0 thought in mind, because we may come back and look at that value here in a few minutes. But this chart doesn't ask you to find anything with the first derivative, so I'm moving on. All right, so now we're going to take this equation and do the second derivative. So we're going to write down the denominator, which happens to be squared, which is a little bit of a pain, times the derivative of the top, which is negative 10, minus write down the top, and the derivative of the bottom is chain rule. You got to put the 2 in front and write down this to the first power, and then take the derivative of the inside, which is 2x. All over the denominator to the fourth, because if you square a square, it goes to 4. So I've got to square this first parentheses out and multiply it by negative 10, which is a little bit, well, it's just a lot to keep up with. So it's easier if you square it and multiply it all as you go than it is to write it down and go back and multiply by negative 10, though. So if I square the first, I get x to the fourth. And then if I multiply it by negative 10, I get negative 10x to the fourth. If I square the last one, I get 16. And if I multiply that by negative 10, I get negative 160. And then if I double the middle, I'll get negative 8x squared. But then if I multiply it by negative 10, I get positive 80x squared. Does everybody follow that, or do I need to talk about that more? I just squared the first, square the last, double the middle. But as I was doing that, I also multiplied by that negative 10 that was on the outside to save some time. Scratch work, whatever you got to do. Sometimes you can do some scratch work over the side if you need to. All right, over here. If I multiply the negative between it and the negative 10x and the 2 and the 2x all together, what will all that make? without the 2x squared. I mean, in the parentheses, just these items outside. Would that be 40x squared? Well, if I do it times this parentheses right here, 2x squared minus 4, 40x squared times each of these, what will I get? Okay. So now, I'm not even talking about the denominator. It's not worth writing it down because it's not changing. I'm just trying to figure out what the top is. So what do we get? Minus 160. All over. And probably factors. I mean, I can at least take a 10 out. And it might factor after that. I don't know. We'll see. All right. If this quartic is going to factor, we'd factor it the same way we do squares. You know, first times the last, do the grouping thing. So 3 times 16 is negative 48. 1 and 48. 2 and 24. 3 and 16. 4 and 12. 6 and 8. The bigger one has to be negative for it to multiply to be a negative and add up to a negative. Yeah, we do have one. Alrighty. So 3x to the 4th minus 12x squared plus 4x squared minus 16. I'm not worried about the 10 right now because it doesn't have anything to do with the grouping process. What can I take out of the first two terms? 3x squared. And that will leave me with x squared minus 4. Oh, wow. And then over here, what can I take out? What, a 4? And that'll leave me with x squared minus 4, so at least we know we're doing it right. 3x squared plus 4 and x squared minus 4. And there was already a 10 in front of that. And it's over x squared minus 4 to the 4th. Yes, you can. You can cancel one of these parentheses out with one of them on the bottom. Now, we already know the bottom gives us vertical asymptotes at plus or minus 2. We figured that out from the original problem. It still shows that, doesn't it? And this 10 can't do anything. He doesn't have an x on him. But can this parentheses be equal to 0? Not unless we want imaginaries, right? So I don't have to worry about a parentheses that comes out with plus in it. I only have to worry about the ones with minus. So the only critical numbers that I get out of this problem are not max, mins, or inflection points at all. I don't have any of those. I just have vertical asymptotes. So now it's time to do our table where we do our interval. Well, it would help if I could spell today. We're just going to put I and V. I'm going to try to save some time. And our derivative information. And our sines. And our concave. So, if we go from negative infinity to negative 2, and then negative 2 to positive 2, and then positive 2 to infinity, we'll be able to tell that these vertical asymptotes down here are doing what on each part. So I'm going to stop the video for just a second and let you calculate up your values, let you pick your values and calculate them real quick. So what are y'all getting in the first section? I assumed y'all used negative 3. Positive. For up. Then that means the next one had to be down. And the last one was up. Not that it has to do that, but that's what this one did, because you said it did the same thing the last problem did. Now, let me talk about that a minute. All right. Look at the original problem. Tell me where the horizontal asymptote will be. Positive 2?
It'd be at 1, right? Because it's x squared over x squared.
Okay, yep, that'll be a 1. Okay, because the powers are equal. Okay, so you're right, it's going to be in 3 parts. Now, the first part is supposed to be concave up, so that means it has to be this shape. I know to put it up there because it can't go up unless it did. If it was down here at the bottom, it'd be going down. Does that make sense? Concave up has to open up and on the concavity. So that means this one over here is going to do this because that's up as well. So the middle has to be down. Now, what did I tell you about that first derivative earlier? 0. So when we go back and look at this first derivative, this problem would have took up the whole board. When set negative 10x equal to 0, we found out x is 0 is a max or a min. Now, in this problem, if you plug in 0, what do you get? Negative 1/4. Okay. It has to open down. What did that cause? All right, now let's think this through. In that chart, 0 would be in this section, right? And 0 comes out negative. And that means it has to be concave down. And the other way it can be concave down on both sides is if it's a max. So if I had done the first and the second derivative chart, it would have showed a lot more information. But with just doing the second chart, I still have enough information to see why 0 has to be a max. All right, now, that's probably a good place for me to stop today in some respects because, and I know I haven't done very much, but the rest of the lesson, I just think I'd like to save for the people who are out because it's more involved. So your homework tonight is going to be really short and you have enough time to actually get it done. This is going to be for 3.4, page 184. Page 184. I would like you to work 2 through 6 even. But instead of looking at the graph in the book and giving me the answers to the questions, I want the derivative work done with the chart, and I want you to match it to see if it matches what your graph shows after you've done it. Okay? All right. Because that's kind of what you would do with that anyway.